We've looked at the trapezoidal rule in a number of different ways in the last number of videos. We're going to look at it once more before finally consigning it to the dustbin, and we're going to look at something known as the recursive trapezoidal rule. So let's go back and have another look at the whole idea of NewtonCotes. There are two basic cases when we can use numerical integration. The first is when we have tabulated data and we have absolutely no option, we have to use it, or when we've got some kind of known function. So for tabulated data, for example the data that we got down there, we don't know what the function is, so we have to use the numbers in the table. If, however, we have a function, we can calculate the function values anywhere we like, and by that I mean the integrand of this function here. So we can put in any value of x and calculate that. Now we saw previously that the global error in the composite trapezoidal rule is given by this expression, that the error scales like the width of our interval, and usually b and minus a are fixed. H squared is our interval size, and we have an option of changing that, and it scales like the second derivative in some way, although we don't know how big that second derivative might be. But we say that the error scales like of order h squared. So the more segments, the smaller h is, and the lower the error, at least within certain bounds. As we saw previously, if we make too many segments, we then begin to see the effect of round-off error. But within limits, the more segments, the lower the error. So one of the questions that arises, of course, is, well, we might know that the error scales like h squared, but how can we estimate how big it is if we don't really know anything about the second derivative of the function that we're trying to integrate? One answer to this question might be to calculate the integral with a successively larger number of segments. So we start off with one segment, we call that I1. We then go for two segments, we call that integral 2. 4 segments will be integral 3, 8 segments, integral 4, etc. And each time we double the number of segments. Then the difference between successive estimates is an estimation of the error. It's not exactly the error, but it gives us an idea of the magnitude of the error. So the error at level n is approximately equal to in minus 1. And we keep on increasing n until the difference between successive estimates drops beneath a specified tolerance. That would be one way of estimating the error. It's good in theory, but if we go through an operation count, we can see that maybe it's not so great in practice. So at level I, the composite Simpson's rule requires I plus 1 additions and 3 multiplications, and that gives us order I operations. So if we start with one segment and go 2 segments and 4 and 8, and we double this m minus 1 times, this gives the number of operations as being of order 1 plus 2 plus 4 plus 8 plus etc. 2 to the m minus 2 plus 2 to the m minus 1, which gives us of order 2 to the power m operations. And of course this can get expensive if m gets larger and larger. So we can actually reduce the amount of computational work, and so we're going to look at a rather clever way of doing the recursive trapezoidal rule, of doing a trapezoidal rule with increasing numbers of segments. So to begin with, let's consider an example where we have at maximum 4 segments. In other words, we have 5 points. They are points x, a, b, c, d, and e. Our first estimate with one segment trapezoidal estimate is sum 1, or I1, that's what I was calling it previously, is just equal to half the width of the element, and that's xe minus xa divided by 2, multiplied by the sum of the function values at a, the function value at b. And that then gives us the area of that complete trapezoid. So note that the step size here is given by xe minus xa. That's when we're looking at it with just one segment. So our first estimate was that comes from the previous slide. Let's look at a second estimate where now we're going to use a step size of xe minus xa on 2, and so we're going to use 2 segments represented in the figure there. We're going to use the values at fa, fc and fe, and it's pretty easy to show that this composite trapezoidal rule with both these two segments here is given by this function here. This term here represents the first trapezoid, that term there represents the second trapezoid. Now, because we've halved the interval, xc minus xa is actually equal to just 1/2 of xe minus xa. Likewise, xe minus xc is just equal to 1/2 of xe minus xa. Therefore, we can replace these terms here with 1/2 xe minus xa, and if you care to do this, not pretty hard to show that the sum for the two segment trapezoidal rule is equal to xe minus xa on 4 multiplied by the function value at a plus the function value at e plus xe minus xa on 4 multiplied by twice the function value at the center point. Now we can see something quite interesting here, and that is that this term here and this term here are related, except in sum 2 it's only equal to 1/2 of sum 1. So we can actually rewrite sum 2 as being sum 1 divided by 2 plus h on, well, that's actually equal to h multiplied by f of c. So we can calculate sum 2 based on what we've already done for sum 1, plus adding in one extra term. So sum 2 is given by this. We just calculate that on the previous page. Let's now go to a 4-segment approximation. We're going to use all of the points that we've got. Our third estimate now has a step size h of xe minus xa on 4. So therefore the h on 2 out the front looks like xe minus xa on 8. These are then the sums for each of the individual trapezoids. If we group all of those terms together and mess around a little bit, it's very easy to show that sum 3 is equal to 1/2 of sum 2 plus xe minus xa on 4, that's the new step size h, multiplied by a sum of fb and fd. That's this point here and this point here. Those are the two new points that weren't in the previous sum 2. So what we can see is a pattern is starting to emerge from this process. So in general, we can write that sum I plus 1 is equal to sum I on 2 plus the total range of our integration, so that's x end minus x naught, divided by 2 to the power I, times the sum of the new function values that we have to introduce to increase the number of segments. What that means is we only need to calculate the values of the function at the new points and add these into the existing sum. We don't need to do the sum for every single point each time we double the number of intervals. For the ith iteration, there are 2 to the I intervals and 2 to the I minus 1 new points and additions into the sum. Plus, there's a few more multiplications and a couple of additions, but it turns out it's of order 2 to the I minus 1 operations at that level. And if you start with one segment, you double the number of segments m minus 1 times, the number of operations scales like 2 to the m minus 1. So that's half as much work as doing the non-recursive trapezoidal rule. The key point from this video is what recursion is. And recursion is basically going through the same process at different levels using the results that you've already got. And in particular here, how can we use recursion to improve on the basic trapezoidal rule? Now, it doesn't give us a better estimate of the integral, but it does cost us less computational effort. We're going to move on a little bit later and come to some even more sophisticated techniques that actually improve the order of accuracy as well. And there's a short list of further reading on some of the integration topics that we've looked at over the last few videos.